Okay, let's look at parametric curves and their derivatives and their arc length. This is sections 9.1 to 9.3 in the official AP Calculus course description. And if you need to print the sheet that I'm using for guided notes, you can go to this bit.ly link down here. So let's talk about parametric curves, and I'm going to first go over a quick recap of what parametric means. Compared to traditional rectangular equations. So your normal way of graphing, I say normal kind of loosely, who knows what normal is, but in traditional rectangular graphing, you have a vertical axis, you have a horizontal axis, they are perpendicular, and the values of the vertical axis depend on the horizontal axis, and that is almost always y equals a function of x. You could obviously use other variables, but typically we have a y and an x axis. Parametric curves are still graphed on the exact same two perpendicular axes. However, instead of the vertical axis being dependent on the horizontal axis values, we introduce a third independent variable that makes both the vertical and horizontal axes dependent on that third. And we typically write parametric equations in the form y equals f of t and x equals some other function of t. And t is your independent variable. X and y will depend on those values of t. And again, you can use other variables. It does not have to be x, y, and t. It just has to be two variables who are dependent on a third independent variable. So let's really quickly recap some graphing. And I'm going to go over this kind of quickly because this is a review. And so I have three graphs, three parametrically defined graphs that we're going to put on paper. We have x equals t, y is t squared. Now you can do something called removing the parameter. And if you substitute, if x and t are the same, you substitute x in here. And it turns out that this will follow the path of y equals x squared. What you don't want to do is assume that if removing the parameter gives you y equals x squared, then that is the graph of your parametric curve. Because parametric curves have more information than simply what path you are lying on. They also can indicate direction of travel. And in this particular case, if you plug in, say, -2 for t, then your x coordinate is -2. So if I go to -2, that's supposed to be -2. Then I'm up here, and this is when t is -2. If I plug in -1, then x is -1. So I'll go to -1, and this is when t is -1. And if you look at the y's as well, -2 squared is +4. -1 squared is +1. And we can keep following this along. And it turns out that this curve will travel in this direction. And so parametric curves do have a very specific direction. We do actually trace this path of y equals x squared, and we're just going to pretend I traced that. That is quite horrible, but that's okay. Hey, right side was okay. And so that is your path of the parametric curve. And so do remember that parametric curves do have a very specific direction of travel. It's not just the path that you are sitting on. So let's look at another one. This one's almost the same. We have x equals -t and y equals t squared. Again, if you remove that parameter, you have the same path of y equals x squared. However, this time, as you start plugging in values of t, starting with, say, -2, if t is -2, well, now your x coordinate is going to be +2. So we're actually starting over here, and this is when t is -2. And as you continue plugging in values of t, we are actually going from right to left. And so this is going to follow that same path. But as you investigate your values of t, we will follow that entire path of y equals x squared. But this time we are going in this direction. We're going from right to left. This is when t is going to be 0. As t becomes positive, we will continue moving to the left and up that way. Not beautiful, but there's, like I said, I'm going to do a quick recap of the graphing. And the last one, x is sine t, y is sine squared. Again, if you remove the parameter, we have the exact same path of y equals x squared. But this one does something a little bit more interesting because if you know your sine graph very well, you should know that sine is always contained between -1 and +1, which means my x coordinates will always be contained between -1 and +1. So while we do sit on the path of y equals x squared, this graph, this parametric graph will always be between x equals -1 and x equals +1. And similarly, your y coordinates, if it's sine squared, will never be negative. So we're going to bottom out at 0. And the absolute largest y can be is +1, which follows what we would expect based on my x constraints. And then as we start plugging in different values and being trig functions, it's convenient to start at 0. If t is 0, then your x coordinate would be 0. So here's where t is 0. We're starting here. If I plug in, and I like to plug in my sexy 90-degree angles, my pi over 2's, and if I plug in pi over 2, sine of pi over 2 is 1. So I'm over here when t is pi over 2. So we start going this way, but then if I go to my next 90-degree angle, so working my way around the unit circle, if I get to x equals pi or t equals pi, then x is back to 0. So we actually come back here at t equals pi. At t equals 3 pi over 2, we will be over here at an x coordinate of -1. And so we're going to come over here. When x is 2 pi, we're going to be back at the origin. And this guy, without any domain restrictions, is just going to rock back and forth, back and forth, back and forth. Like an old kid's book. So anyway, so that one is an interesting curve because it does follow on the path of y equals x squared, but we are only looking at this bottom piece down here. As a matter of fact, I could go ahead and just get rid of these little tails coming up here, extending beyond y equals 1. And so there's a quick, what I thought was going to be quick recap of parametric graphing, but let's get into the calculus. And I'm not going to give you generic notes on the calculus. I think it's best if we just did some examples, starting with the classic calculus question of find the equation of the line tangent. I'm going to stop right there for a second, because anytime you see that question, you should immediately be thinking that we need a point and a slope. Every single time you write the equation of a line, you will need those two pieces of information. So we continue reading to the parametric curve. Ooh, that's different. It's no longer rectangular in the traditional sense. See, we are concerned when x is equal to 2. So I know my x coordinate of my point is 2. My slope, I'm going to get to that in a second. To get my y coordinate, well, y is t squared minus t, but I have x equals 2. I need to find my t that gives me the x coordinate of 2. And so I will simply take that x coordinate, which is t cubed plus 1. I will set that equal to 2. You solve that, and we get t is equal to 1. And so I have my t value. Now my y coordinate at time 1 is going to be 1 squared minus 1, which is 0. So I finally have my ordered pair 2, 0. The slope, however, is where it gets a little bit interesting because just like we always have, to get slope, we need a change in y over a change in x. And in calculus, that is turned into a dy over a dx. And the problem here is my x's and y's are both defined as a third variable. They're functions of a third variable of t, but this is not going to be too bad. And I am going to give you, I guess, a few generic notes here. So dy dt, dy dx, we're going to take advantage of some properties of Leibniz notation, and that is that it does behave like a normal fraction. If I take dy dx dt, and I divide it by the derivative of x with respect to t, well, if you divide fractions, you can flip the denominator and multiply by its reciprocal. So dy dt divided by dx dt is the same thing as dy dt divided by dt dx, multiplying by the reciprocal of that denominator. The dt's will divide out, and you are indeed left with dy dx. So I kind of went in a big circle, but dy dx, you simply divide the derivative of y by the derivative of x, and it's very convenient for that first derivative. Therefore, for this particular problem, dy dx is going to be the derivative of y with respect to t, which is simply 2t minus 1, over the derivative of x with respect to t, which would just be 3t cubed. And if I want my slope at t is equal to 1, that would be my derivative such that t is equal to 1, which gives me 2 times 1 minus 1 over 3 times 1 squared, which is 1/3. And I finally have my slope of 1/3. And then the last simple step, write the equation of the line tangent. I like point slope form. Y minus my y coordinate of 0 is 1/3 of x minus my x coordinate of 2. And there is our tangent line at the point where x is equal to 2. Let's go on and look at number 2. If x is this and y is that, what is dy dx? And again, dy dx is simply your y prime divided by your x prime. So dy dx would be dy dt divided by dx dt. The dt's will divide out, leaving you with that dy dx. dy dt is 6t squared. dx dt is 2t. And then that will reduced to 3t, and that's it. Hey, very nice. Isn't that nice? Isn't that nice? Very clean, very clean. But then we have the second derivative of a parametric curve, and I am asking at a very specific point, t equals 1. So let's see how this happens. Unsurprisingly, to get to the second derivative, we will first have to find the first derivative. So dy dx would be the derivative of your y expression, which is 4t cubed minus 6t squared, divided by the derivative of your x expression, which is 2t. So there's my dy dx. Now I need to get the second derivative. And to get the second derivative, you always pause and think algebra. Never just dive into calculus. Always look and think if there are ways you can clean this up and make it a little bit easier. And we indeed can do that. I can factor out a 2t from the numerator. That will leave me with 2t squared minus 3t. I could have factored out a second t, 2t squared. However, I only chose the 2t because that's what I have in the denominator, and I wanted to divide those away. So I have a cleaned up first derivative of 2t squared minus 3t. Now we need to get to the second derivative. And here's where you have to be really careful, because a lot of people are not going to be paying attention, especially when you're new to this, which I assume you are. And they will say the second derivative is 4t minus 3, because you're doing the power rule to that nice little quadratic 2t squared minus 3t. And you have made a mistake, because we are differentiating with respect to x. This is why I love Leibniz notation over the f prime, y prime type notations, because Leibniz tells you explicitly what your independent variable is, and I am differentiating with respect to x. T is not an x, which means my second derivative of a parametric curve must be done implicitly. So we will differentiate 2t squared like we normally would, which is 4t. However, because t is not an x, we then have to multiply by dt dx. I will repeat that with negative 3t. That would be a derivative of negative 3. Again, t is not that independent variable of x, so I must multiply by dt dx. And to make this a little bit easier, I'm going to factor the dt dx out, so I only have 1 to wrestle with. And so there is an expression for my second derivative. But then we have this dt dx. What can I do with dt dx? Well, I have x here, and I could come up here with x. And if x is t squared minus 1, then that means dx dt, the derivative of x with respect to t, would just be 2t. And I don't need to implicit that because I am differentiating with respect to t. And the beauty of Leibniz, it behaves like a fraction. It does. So if dx dt is 2t, well, I can flip both sides, raise them to the negative 1 power. That means dt dx would equal 1 over 2t. And now that I have an expression for dt dx, that can substitute in and replace the dt dx in my second derivative expression down here. And now I have a cleaner second derivative expression in terms of only t, and that is this expression. And now that I have that, I can plug 1 in. Don't forget, we are plugging 1 into this. So my second derivative, d squared y over dx squared, such that t is equal to 1, is going to be 1 over 2 times 1. I remember my 1 times tables. That's 1/2. 4 times 1 minus 3. That'll be 4 minus 3 is 1. And half times 1 is 1/2. So your second derivative of a parametric equation is an implicit differentiation problem. Okay, now having done all of that with the implicit differentiation and substitution process, there is a memorized formula that you can use for the second derivative of a parametrically defined function. And it is this, that if you want the second derivative, you can find the derivative with respect to x of your first derivative, dy dx, and divide the whole thing by dx dt. I am very bad at memorizing formulas, and if I tried to use that, I would mess it up somehow. To me, it's easier, or maybe I should say safer. To me, it's safer to actually go through the implicit differentiation process find out what dx/dt is, flip it to get dt/dx. It is a little bit longer with the way I showed you initially. I feel it's safer though, because if I'm just trying to go with rote memorization, I very often misremember little bits. And if I do it more mathematically, like I did the first time versus with memorization, I feel it's a safer approach. But if you are big into memorization and you want to memorize that formula, it does indeed work. Just make sure you use it correctly. And then I have one more thing I want to talk about, and that is how we can do arc length with parametrically defined functions. And this is getting into section 9.3 of the course description. And arc length, which you hopefully have already had some exposure to in the world of rectangular curves. And the formula for arc length in the rectangular world is the integral from a to b of the square root of 1 plus the derivative of your function squared. And that is your old rectangular arc length. And do remember that the rectangular arc length is derived from the distance formula. It's a change in x squared plus a change in y squared. In the world of calculus, that becomes the derivative of x squared, and the derivative of x would be 1 if we have y equals f of x. The derivative of y squared would be your f prime of x squared, and then we apply an integral to that to get arc length. And we're going to do the exact same thing for a parametric curve, and it's pretty nice. If you know your rectangular arc length, parametric is a tiny little tweak, which is why I'm adding it to the end of this lesson. And it is this. It's the square root of your f prime squared plus g prime squared. And I do have up here your f and g are your expressions for y and x. So you could look at this as f is y prime squared, g is x prime squared, which again goes back to your change in y over your and your change in x in the distance formula. So there is your parametric arc length formula. I'm going to do a whopping one example with that, and we will simply set it up. And then after setting it up, we will use a calculator to compute the actual arc length. And so I know I will need the derivative of y and I will need the derivative of x. Hopefully neither one of these are going to be crazy difficult, the derivative of y. And we are differentiating with respect to t here. So dy dt, or y prime, would be 1 over t. The derivative of your x expression would be 2t. And then we simply roll that into our definite integral, 1 to 5. And I gave you the values of t here. One thing to look out for is make sure that you are looking at values of t. They could give you values of x. They could say for x is between 1 and 5, and then you would have to go back to your x expression and find out what the values of t are that give you those x bounds. But in this case, I made it a little bit nicer by giving you the values of t. And so derivative of y, 1 over t squared, plus the derivative of x, which is 2t squared. And we will simply throw that in a calculator, which these are typically calculator problems because they usually give you some really crazy antiderivatives that are difficult to do or near impossible to do by hand. So they will either ask you to set it up and run away from it or use a calculator. It is possible it can be done by hand in very carefully chosen functions. But here's what I got the first time I punched it in my calculator. And I started to just not even include this in my lesson. But if you have a CAS-capable calculator, and I'm using the TI Inspire CAS, it can often give you exact answers that are really ugly. And while that would be acceptable on the AP exam, don't do that. Don't make your readers hate you. So please just hit Control-Enter to force the decimal, and we get a decimal of 24.1175. And I am going to include that fourth decimal while on the AP exam. You don't need to go to 4 decimals, but I'm putting that there because you can use the standard rounding procedure of rounding up, or on the AP exam, they will accept that truncated version of 24.117. And there is an introduction to parametric derivatives and arc length.